Hello everyone, my name is Changchun Zhou. I am pursuing my PhD degree in Peking University Shenzhen Graduate School. The title of my talk is An Energy-Efficient, Low-Latency, Three-Dimensional Convolutional Neural Network Accelerator Leveraging Temporal Locality for Zero-Skipping and Hierarchical Node Balance. I will give my presentation from the following four parts. Firstly, I will give a brief introduction to the 3D-CNN. Many complicated computer vision tasks, such as video classification, require feature extraction from the entire sequential images rather than each individual frame. 3D-CNN has been proved to be more effective in these tasks compared to the conventional 2D-CNN because 3D-CNN directly extracts spatial-temporal features from the video. This is the computation process of 3D convolution operation. Based on 3D convolution operation, C3D, a 3D thing for classifying actions in videos, illustrated an important figure consists of 8 convolution layers and 3 fully connected layers. The input for 3D-CNN is a sequence of consecutive frames. There are plenty of overlaps between any two consecutive frames, which is the temporal locality. If we subtract the back frame from the front frame, the temporal differential frame is obtained. The sparsity of differential frames is higher compared to the raw frames, so that zero skipping saves storage burden, energy consumption, and computation time without accuracy loss. We expand the temporal differential method to other applications. A variety of 2D-CNN accelerators have explored skipping zeros in each activations or waits. Concluding investigates the sparsity in activations, but the computation cycles are unfortunately not skipped. SCN explores sparsity in both waits and activations by using the sparse planar-tiled input stationary Cartesian product data flow. To improve the storage efficiency, Sticker proposed a multi-mode hierarchical data memory, which can be reconfigured for networks with different sparsity modes. For video applications, Morph, a 3D-CNN accelerator, can adaptively support different spatial and temporal tiling strategies. Systolic Cube, a 3D Systolic Cube architecture, explores the spatial and temporal localities of 3D CNNs, but both of them don't leverage the sparsity. The major contributions or work are listed in this slide. We proposed an energy-efficient, low-latency 3D CNN accelerator. A threshold-based differential frame sparsity enhancement method is proposed to increase the sparsity of differential frames by dropping out small differential values. To skip both the redundant operations and redundant computation cycles for a wide sparsity range of activations and width, a full zero-skipping microarchitecture is proposed. To address the load imbalance issue after skipping zeros, a hierarchical load balancing scheme is proposed. The details of proposed 3D CNN accelerator are introduced in Part 2. There are 16 PEs. each of which contains 27 macros and a scheduler. The activations are pipelined and the waves are broadcasted to PE array. This is the computation flow of each PE. First, initialize partial sum memory to 0. Second, calculated the first input feature map using raw data, while computing the rest using the temporal differential input feature maps one by one. Third, the data are propagated in cascaded fashion with just a single addition. The addition propagation from partial sum to partial sum memory 3 is to restore raw partial sums. Finally, calculate the raw output feature maps. To obtain better power performance and area, we propose 3 techniques. The first is threshold differential value dropout. In the shallow convolution layers, small differential values take a large portion and don't improve the quality of feature extraction. Therefore, those small differential values could be dropped out without accuracy loss. The amount of activations is significantly larger than the amount of waves in the shallow convolution layers. Therefore, as the figure shown, dropping out the small differential activation values in the shallow layers could increase the activation sparsity significantly. Compared to previous zero-skipping methods, we hope to skip not only the invalid computation operations and cycles, but also fetching and storing invalid data. Therefore, a flag-based 4-0 skipping architecture is proposed. A bitwise AND of the activation bit vector and wait bit vector is performed to get an AND bit vector, which indicates where the activation and the wait are both non-zero. These ones that are behind the first one in AND bit vector are dropped out. Finally, the number of the left ones indicates the bias of the activation and wait in the sparse register file, respectively. The proposed threshold differential value dropout and distiller pruning introduce numerous zero activations and waits, respectively. The proposed 4-0 skipping microarchitecture reduces the number of convolution operations dramatically by skipping invalid multiplications. Load imbalance is caused by different sparsity at the same time among max and among PEs. To address this issue, we propose a hierarchical load balance method. The intra-PE load balancing is to balance loads among 27 max in a PE. The computation flow of the proposed PE is similar to weight stationary data flow. The whole function of PE is a convolution of 16 rows of input feature maps and 27 waves. A task is defined as the convolution of a 32-channel weight with a row of 16 32-channel activations. A scheduler is designed to allocate new tasks to idle max. The scheduler provides which row of activation, which weight, and which partial sum register file are allocated to the idle max. The method is with low hardware and energy overheads due to the compatibility with the proposed flag-based microarchitecture. The 16 PEs share the same activations, but they perform convolution with different filters. After applying intra-PE load balancing, There exists a strong correlation between the sparsity of a filter and the convolution time. Filters are sorted in the descending order of their sparsity. The adjacent filters are divided into groups, each of which contains 16 filters allocated to 16 PEs. Therefore, the calculation time is close among PEs. The green triangle represents the convolution time savings without any hardware overhead due to only adjusting the order of the channels offline. The next part is the experimental results of our design. The basic experiment setup is given in this slide. UMC 55 nanometer low-power CMOS technology is adapted in our design. A cadence genus is used for logic synthesis at 100 MHz and 1.08 volt supply voltage. The benchmark is the 8-bit C3D network classifying UCF 101 dataset. The effect of the proposed three techniques is shown in the slide. All techniques have good performance. As a result, the accelerator obtains the energy efficiency of 4.66 TOPS per watt and the speed up of 9.89. For different sparsity of activations and widths, this is the experimental results of the accelerator's generalization ability and peak energy efficiency. The energy efficiency is increased monotonically with increased sparsity and up to 17.2 TOPS per watt. The performance comparison of the proposed 3D7 accelerator with the state-of-the-art accelerators is shown in the slide. Compared to Iris, the proposed work has 13.3 times improvement of energy efficiency and 12.2 times speed up. Compared to Sticker, 1.6 times improvement of energy efficiency and 1.4 times speed up are also obtained. The performance comparison is detailed in the table. You can refer to our paper. Finally, I'd like to conclude my talk today. An energy-efficient, low-latency 3D CNN accelerator is proposed in this paper by deeply exploiting the sparsity in the neural networks. A threshold differential value dropout method is proposed to increase the sparsity of activations in the shallow convolution layers. A full zero-skipping microarchitecture is proposed to skip both the zero-valued activations and widths to speed up and energy savings. A hierarchical load balancing scheme is employed to solve the load imbalance among PEs and among cycles after zero skipping. In the end, the proposed accelerator achieves an energy efficiency of 4.66 TOPS per watt and a latency of 0.17 seconds. While running C3D with UCF 101 dataset at 100 MHz with 1.08 volt supply voltage, the proposed accelerator achieves higher energy efficiency and faster speed compared to the state-of-the-art, thereby providing an attractive option for edge computing. Thank you for listening.